Chapter 6.1. Now in Chapter 6 we're going to be having a discussion on normal distributions. Now the key word here is normal. We've already talked about probability distributions, and distributions refers back to the distribution shapes that we discussed in Chapter 2. And that refers then back to histograms. Try to get all of these in the best that I can. All right, so I've already constructed all the different types of distribution shapes that we talked about in Chapter 2. Here is a symmetrical, which is more or less the same on both sides if you were to fold this in half. We have skewed left and skewed right. We have uniform, and then we have bimodal. Now, of these 5 different distribution shapes, one of these is what we call a normal distribution, and that's what we will be confining our discussion to. And the one that is the normal distribution is the symmetrical. And the reason that is because if you were to connect the top of the bars, it would create what we also know as a bell curve. Most of you all have probably heard of a bell curve or bell shape. So the symmetrical in Chapter 6, we will only be using our discussion for normal distribution, which means it comes from a symmetrical bar graph. Now, in your book, it gives a picture of a bar graph on page 251, figure 6.1. So you can look at that, and these are the characteristics of a normal distribution, a normal curve. It's bell-shaped. Its highest point is over mu, which is in the middle. It is symmetrical, which means it's the same on both sides. The curve approaches the horizontal axis but never touches or crosses it. Then they have what are called inflection points. And this is of great importance too that we'll discuss a lot about, is the area beneath the curve and above the axis is exactly 1 or 100%, meaning 100% of the data is shown in that normal curve. Now, that picture on page 251 shows the normal curve. So let me get this up here. All right, so I've drawn a normal distribution or a normal curve. It's bell-shaped, it's symmetrical, meaning half is to the left, half is to the right. And then I have it broken up into this that cuts it right in half is known as mu. So for this particular problem, it says let mu equal 2. So the value here at mu, which remember mu is the average, okay? It's the population parameter, it's the mean, it's an average. So if this vertical line was representative of the value of 2, and then it tells us our standard deviation is 5. So if you'll notice that as we go to the right, we add a standard deviation each time. So if I start at 2 and as I go to the right, I would add the standard deviation. So 2 plus 5 would be 7, and then I would add the standard deviation again, so that would be 12, and then I would add another standard deviation, which would be 17. So as you go to the right, you add the standard deviation. As we go to the left, we subtract a standard deviation. So 2 minus 5 would be negative 3, minus 5 would be negative 8, minus 5 would be negative 13. So those would be the values in this particular problem that would be represented on mu and then on your standard deviations. Now, the area under the curve, all of this represents 100% of the data. And for a normal curve, it breaks it into such as mu is what cuts it in half, so that means 50% of the data lies to the left, 50% lies to the right. Then what we also see on that picture in the book is it tells us that between mu and 1 standard deviation, 34% of your data falls here, and this is symmetrical, so it's the same on both sides, or in decimal form, that would be 0.34. Now, one of the things in this chapter is if it's talking about or asking you to find the area, you leave your answer in percentage form. If it asks you to calculate or find the probability, then you leave your answer in decimal form. Then the amount that is between 1 standard deviation and 2 standard deviations is 13.5%, or 0.135, which again, it's symmetrical. So it would be the same on this side. Then the amount between the 2nd and the 3rd standard deviation is 2.35%, or 0.0235. I don't know if I'll do this because I'm left-handed, so and then we have left what are called the tails. Now, they don't always show the amount of the tails in the book. So basically, if you were to add 34% plus 13.5% plus 2.35%, you would get a value that is not yet 50%. It would be 49.85%. So that means that what is left is the tail is 0.15%, or as a decimal, 0.0015. So you have to be sure that you don't forget about the area, even though it is very small, that is in the tails. Now, as long as you have a normal distribution or a normal curve, which is what we're talking about in Chapter 6, so we always will, then these percentages remain the same. It doesn't matter what problem that you're doing, these percentages from mu to 1 standard deviation is always 34%. So we will be using these percentages and these probabilities. Now, the empirical rule, which is discussed down here, it tells us the amount that is within 1 standard deviation is 68%, within 2 standard deviations is 95%, which within 3 standard deviations is 99.7%. Well, what that is saying is within 1 standard deviation, here's mu, so here's plus 1 standard deviation, minus 1 standard deviation. So within 1 standard deviation is this right here, which is your 34% plus 34%, which is the 68% that it was talking about. Within 2 standard deviations would mean to go 2 to the right and 2 to the left. So if you included all of this, that's your 13.5 plus 34 plus 34 plus 13.5, so that's a total of 95%. And then within 3 standard deviations would mean include these as well, so the only thing not included is the tails. So if you added all of those up, you would get 99.7% of the data falls within 3 standard deviations. Now, we've already talked about this, but at the very bottom of this, it says the book leaves out the percentages of the tails. Each end of the normal curve contains approximately, and we already talked about that was 0.15% or 0.0015 if you looked at it in decimal form. So do not forget about those because they will come into play when we actually do calculations. Before we start applying this information, I just want you to get familiar with drawing curves and finding the area or probability. And again, if it asks for area, give your answer as a percentage. If it asks for probability, give your answer as a decimal. So it says use the empirical rule. So this is talking about use those percentages we just looked at on the last page to answer the questions. Draw the curve. You'll notice I've already drawn the curve. Shade and calculate how much of the area or probability under the curve is between the vertical lines. All right, start with this first one. So I already drew a curve, okay? And it says have your vertical lines at mu, which I have mu, and mu plus 1 standard deviation. Then if we were to shade this, it is saying how much area is there between these two lines. Well, if we go back to the table that we just looked at on the last page, between mu and mu plus 1 standard deviation on a normal curve is always 34%. So the area is 34%. If you were to give your answer as a probability, it would be 0.34. And the problem will specify. It will ask you what is the area, or it will ask you what is the percentage. So just take it by however the question is asked. Okay, here's the second one. So here's mu minus 1 standard deviation. So that's that vertical line, and mu, which is this vertical line. So then I'm going to shade that area. And then using the empirical rule in the table that we looked at on the last page of notes, this is also 34%. So the area would be 34%, or as a probability would be 0.34. So these have the same area, it's just one is on the plus side and this one is on the minus side. All right, let's look at some additional examples. All right, so I've drawn the normal curve, and my vertical line or boundary lines are going to be mu, which is right here, and then mu plus 2 standard deviations. So I went over 1, 2, and I drew the vertical line. So now I am going to shade the area between these two. So when I look at my table, it tells me that this is 34% and this is 13.5%. So to find that area, we would add those, 34% plus 13.5%. So the total area that we have shaded is 47.5%. Or as a probability, that would be written as 0.475. All right, I have my normal curve drawn, mu minus 3, so I went over 1, 2, 3, and mu. So now I'm going to shade everything but the tail. So what we have shaded is 34%, 13.5%, and 2.35%. So we would add 34% plus 13.5%. Just a second, I think my pen's starting to run out of ink, which is not good. Plus 2.35%. So when we add all of those, that gives us 49.85%. And again, as a probability, that would be 0.4985. Now, in this particular problem, what we've done is completely correct. You'd get full credit, but an alternative way is, if you were to find the area, you could recognize that this tail is 0.15%, and the whole half of this is shaded except the tail, so you could have done 50%, which is from mu all the way to the left, minus, sorry, not an equals there, minus the tail that is not included, and you would have gotten your 49.85% as well. So there are alternative ways to calculate that as long as you have an understanding of your areas. Okay, let's look at the last two that I have here. All right, so here's my bell curve. Mu minus 1 standard deviation. So here's mu minus 1 standard deviation, and here is mu plus 2 standard deviations. So we are finding, or it's asking us to find the area here. So again, we have 34%, 34%, and then we also have 13.5%. Now, we talked about the empirical rule that said within one standard deviation is 68%. So if you recognize that, or obviously 34 plus 34 is 68%, plus the 13.5%. So you add those together and you get 81.5%. As an area, as a probability, we would write it as 0.815. All right, over here we have mu plus 1 standard deviation and mu plus 3 standard deviations. So in this one, it's asking us for that shaded area. Well, we know this is 34, this is 13.5%, and this one is 2.35%. So when you add those together, you get 15.85%. So 13.5% plus 2.35%, and that is 15.85%. Or 0.1585. All right, so that's just some general bell curves, how to find the probability of those. Now what we're going to do is we're going to look at a problem which takes that information and actually applies it to a particular life application type problem, which is our ultimate goal, is to be able to apply this information. All right, the problem reads, the amount of coffee dispensed by a coffee vending machine normally distributed. Okay, that is very important that it says normally distributed, because that tells me the bell curve works. That tells me those percentages of 34%, 13.5, 2.35, and 0.15 work in this because it's normally distributed. If it wasn't normally distributed, we could not apply this information. It tells us that we have a mean, or mu, population parameter. Mu equals 7.6 ounces. So that tells me mu, which is right here, is 7.6 ounces. That is the average. Anything to the right would be above average. Anything to the left would be below average. And it has a standard deviation of 0.4. So remember, as we go to the right, we add 0.4. So 7.6 plus 0.4 would be 8, or 8.0 ounces. Add 0.4 again, we would get 8.4 ounces, and add 0.4 again, we would get 8.8 ounces. And then as we go to the left of mu, we subtract our standard deviation. So 7.6 minus 0.4 would be 7.2 ounces, minus 0.4 would be 6.8 ounces, minus 0.4 would be 6.4 ounces. So this is talking about how many ounces are poured into the cup at a vending machine. This is average, 7.6 ounces, okay? Then it asks these problem-specific questions. It says, find the probability that the cup or the vending machine will overflow an 8-ounce cup. Okay, so the probability that it overflows or is greater than 8 ounces. Well, greater than 8 ounces would be that area right there. So, since this is a normal distribution, then I can apply and go, oh, well, I know this is 13.5%, this is 2.35%, and this is 0.15%. This is talking about probability, so I am going to look at those values in decimal form. So I'm going to add 0.135 plus 0.0235 plus 0.0015. So when you add all of those together, then you get 0.16. So what that means is the probability that the cup overflows is 0.16. What does that mean? 16% of the time that vending machine is going to overflow the cup. Now, this part C reads, find the probability that it won't overflow. Well, not overflowing means anything less than. So that would be everything here to the left? Well, you could add 34% plus 34% plus 13.5% plus 2.35% plus 0.15%, or in this case, what would be a little bit easier is once you recognize that B and C are complements, and complements have to add up to 1, so I can do 1 minus the probability that it does overflow. So that it won't overflow is 0.84. So it overflows 16% of the time, 84% of the time it does not overflow. So then based upon those probabilities, it says, okay, if you had 850 cups, how many do you expect to overflow? Well, 16% of the time they overflow, so I need to find 16% of 850. So I would take 850 times 0.16 in my calculator, and when you multiply that, you get 136, which tells us 136 cups of coffee is going to overflow, which means you're going to have some upset customers. All right, let's look at this next example. Okay. Assume normal distribution. So again, what does that tell me? I can use the bell curve, which I've already have constructed those. Now, we have Doug over here. Doug scored a 57. That's his real life score, so that is an X value. Okay, so he scored a 57 on the Miller's analogy test, so I abbreviated that. And that test has a mean of 50, so I have mu equals 50, and a standard deviation of 5, so I have sigma equals 5. All right, so Doug, it's normally distributed. So if we look at the information, it tells us that mu is 50, and the standard deviation is 5. So this would be 55, 60, 65. As I go to the left, I would subtract 5. So 45, 40, 35. Now, 50 is average. Anything to the right of that is above average. So where is Doug? He's at 57, so he is above average. So he would be approximately right here. So X equals 57. That's where Doug lies on his particular bell curve. Now, what does that tell me? He did above average. He did between 1 and 2 standard deviations. That's what that tells me. All right, then it goes on to talk about Jennifer. So here's Jennifer. Now, she scored a 120. So on her particular test, she scored 120. So you go, wow, she blew Doug out of the water. Well, we can't say that because she took a different test. This different test has a different mean. It has mu of 100. So its average, on average, students scored 100, and it has a standard deviation of 15. So as I go to the right, I would add 15. And as I go to the left, I would subtract 15. All right, so then if we wanted to see how Jennifer did, okay, well, she scored a 120, so she did above average. So she would be about right here. So then it says who scored better. Well, I would look at this and I'd go, well, they both scored above average. Wow, they both scored between 1 and 2 standard deviations. So right now, I can't say with 100% certainty if Doug did better on his test, if Jennifer did. It looks a lot like they did about the same. So that concludes today. So you're going, okay, well, who scored better? Well, when we get into the 6.2 lecture, we'll talk about what we can do to find out who actually scored better, and then I will refer back to this last page of notes in 6.1. But that does complete 6.1 notes.